So here we are going to analyze question number 9. It says how many 4-digit numbers, yes, only 4-digit numbers can be made from the 7 digits, 2, 3, 4, 5, 6, 7, and 9, if no digit can be used more than once. And B, how many of these numbers are less than 5,000? So that's a total of 4-digit numbers, but out of that total, there are some that are less than 5,000, and there are some that are even. So first, let's calculate how many in all 4-digit numbers from the 7. So let's tweak this a little bit, and let's change this to 5-digit numbers. And I add another number, which is 8. So you can use this example to answer the question itself. So we have to identify what is our N and what is our R. Our N is 1, 2, 3, 4, 5, 6, 7. We have 7 digits. Also, it must have been 6 in the other example. So we have to correct that. So now we have 7, or N is 7. Let's verify that again. 1, 2, 3, 4, 5, 6, 7, 8. Oh, 1, 2, 3, 4, 5, 6, 7, 8. I'm sorry for my little counting blunder. So it's 8. So the question was actually correct when it says 7. And our R is 5. So we want to make 5 numbers from those 7 digits. Now, this implies arrangement, selection, and arranging, which is permutations. So I just want to point out the fact that permuting R from N is the same as selecting or choosing R from N and arranging R. Now, and now in mathematics implies the multiplication sign. So we have to take that into consideration. So basically, our N there is 8, our R is 5. So basically, we are going to do 8p 5. It P5, you can simply type this in our online permutation calculator. It P5 is actually 6,020. So that's the answer for part E. There are 6,720 distinct 5-digit numbers that can be made from those 8 digits. Now, part B is asking, out of those 6,720, how many of these numbers are less than 5,000? Okay, so an example would be 2, 3, 4, 5. Yes. One example is 2, 3, 4, 5, 2,345. So how many of them are there? Okay, another example is 4, 3, 2, 5, and so forth and so forth. So we've got to do some fixing is possible. So we have to fix the first digit. So the first digit must be either 2 or 3 or 4, or implies add. Okay, so we have to calculate those that begin with 2, and those that are begin with 3, and those that are begin with 4. Okay, and then we add them together. If we fix the 2, remember no repetition, and we've got 8 digits. So, and we're writing 5-digit numbers, so we need 4 more to complete our 5-digit numbers that begin with 2, and the same goes for 3 and 4. So to calculate how many of those 5-digit numbers that begin with 2 we fix the 2. That means we take all the 2 from the set, the number 2 from the set, and we are left with how many of them now? We are left with 7 of them. Okay. And basically, the set that we are going to select from contains 7 digits because 2 has been fixed. So we are basically going to be selecting 1, 2, 3, 4 from 7 and arranging the 4 because the 2 has to be fixed. You must start with 2. 2 is not being arranged. It has to stay in the first position. Okay. So basically, we are going to randomly select 4 from 7. So that's 840. And you realize now that's the same calculation we are going to get for those that begin with 3 and 4, because what we do, we have to fix the 3, replace the 2, and for the 4 now, we've got to fix the 4, begin with 4, sorry, fix the 4 and put back the 2. Okay, so we always end up with selecting 4 from 7 and arranging 4. Okay, that's basically 7p4 in a nutshell. And that's 3 times 840. And we can rapidly calculate this in our online calculator. 3 times 840 equals 2,520. These are all the 5-digit numbers that are less than 5,000. Now, Patsy is saying how many of those 5-digit numbers that are even, okay? So to be even, you must end with an even number. So here we're analyzing the endings, which are those that end with 2, those that end with 4, those that end with 6, and those that end with 8. Okay, so must be end with 2 or 4 or 6 or 8. That's addition. So let's calculate, for example, those that end with 2. You fix the 2 at the end, and you are selecting 4, 1, 2, 3, 4 from a set of 1, 2, 3, 4, 5, 6, 7. And then you are arranging the 4. Okay, because the 2 has to be fixed at the end. And basically, that's like 7p4, very similar to part B. So we get the same 840, and this 840 seems to apply to those ending with 4, those ending with 6, and those ending with 8. So basically, that will be 4 times 840. And that's 3,360. So that's the answer for part C. Let's take a look at number 10. This question seems to be fairly simple. It says, how many circular rings can be formed from 15 differently colored beads? So we're going to change the number 15. We can say, let's say 12. Okay. And but we're going to keep the condition, which is creating a ring. So to help us for the solution, let's go to the unit number 1 to see what is there with regards to arranging on a ring or like a chain and bracelet. similarly. So here is our list of formulas. And here it says arranging distinct objects on a circular wire string is n factorial over 2n. In the previous recording, we justified the rationale for this formula, the proof thereof. So that's what we're going to use. So we have to identify what is n. N will be is 12. And all the bits are differently colored, so no repetition. If there was repetition, then it has to be divided out. Okay, so this formula can be modified even further. So therefore now, because remember 0 factorial is 1. So if there is no repetition, you can divide by 0 factorial. I'm referring to this formula there, where you have to divide by p factorial, p alike. So if there is nothing alike, you can divide by 0 factorial, because dividing by 0 factorial is like dividing by 1, and your answer is not affected in any way. So if you take a closer look at these formulas, you can actually modify it, improve on it by actually saying this divided by p factorial, that entire thing here, n factorial over 2n divided by p factorial, p are alike, or n minus 1 factorial divided by 2 divided by p factorial. So if there is no repetition, 0 factorial is 1. We are dividing by 1. But here we have all these things, so that's not really the case. Yes, it is the case. We have 0 factorial, we have 0 repetition, so we are going to divide by 0 factorial. Okay, so basically we're going to apply this formula, and we've got 12 factorial. Let's put our fraction. We've got 12 factorial. We can apply the different versions of it, divided by 2 times 12. And this now is going to be divided by 0 factorial. Because here now, the repetitions, let's call it P, is equal to 0. Okay, there are no repetitions. And let's see what this gives us in our calculator. That's 12 factorial divided by 24. Divided by 0 factorial. So that's 12 factorial divided by 2 times 12 divided by 0 factorial. And that's 199,584. Just to prove a point, 0 factorial is equal to 1. Why 0 factorial is equal to 1? What is a 0? 0 is nothing. But here it is saying that 0 is actually something, or nothing is something. If you punch in Google, if you type in Google, what is nothing? What is nothing? That's a highly philosophical word, and it's very debatable. Nothing, nothing, or nothing is the complete absence of anything as the opposite of something, and an antithesis of everything. The concept of nothing has, and it goes on, and trust me, it continues and it explodes from there. Here you have philosophy, argument, and debating. That's a very profound question. But for our case, nothing factorial is 1.